flipped classroom presentation for Further Maths Unit 5, Unbiased Estimators 1. Suppose x is a random variable whose distribution involves an unknown parameter theta that we want to estimate. Then examples of a parameter that we need to estimate could be the success probability of a binomial distribution, the mean or the variance of a distribution, the mean of a Poisson distribution, the sample mean of a population, the mean of a continuous function, and we have a definition that the statistics t is said to be an unbiased estimator of the parameter theta if and only if the expected value of t becomes theta. It's equal to theta, whatever the value of theta. In many situations, it's possible to find more than one unbiased estimator of a parameter. So which one is the better one to use? Well, one obvious answer is to choose the one that is most likely to give a value close to the actual value of theta. Therefore, let T1 and T2 denote two unbiased estimators of theta. So if they're unbiased estimators, then expected value of T1 is theta, as is the expected value of T2. The standard deviations of their sampling distributions will show us how close they are to theta. Then the better estimator would be the one with a smaller standard deviation. The standard deviation of the sampling distribution of an unbiased estimator of t, it's called the standard error and will be abbreviated to SET. It's also equal to the square root of the variance, as is the standard deviation. A reminder, expectation algebra. So the variance of x, you should remember, is equal to the expected value of x squared minus the expected value of x all squared. And if we have a linear combination of x, so an expected value of ax plus b, I can take the expectation in to give us a times the expected value of x plus b. And the variance of that, well, you square the coefficient and disregard the b because that does not vary. So square the variance for the variance of the combination. If we have two variables, as in z equals ax plus by, then the expected value of that combination, I can take the e in, so I've got a times the expected value of x plus b times the expected value of y for any distribution. But for the variance, x and y need to be independent variables. So the variance of x would be, I square the coefficient, so a squared times the variance of x plus b squared times the variance of y. And that's been done before. So let's see if we can use that information. Example 1. Let x1, x2, x3 denote a random sample of 3 observations of a random variable x whose mean is mu and whose standard deviation is sigma. Show that the two statistics, T1 there and T2, are both unbiased estimators of mu and determine which of them is the best estimator. And then write down the linear combination of x1, x2, x3, which will give an unbiased estimator with a minimum standard error. Express this minimum standard error as a multiple of sigma. So first of all, we need to show that the expected value of T1 and the expected value of T2 are unbiased estimators of mu. We are given that x, expected value of x is mu and the standard deviation of x is sigma. So expected value of T1 first. So expected that value of that combination, I can take the E in. So I've got 1/6 times the expected value of x1, and then 2/6 times the expected value of x2, plus 3/6 times the expected value of x3. Each expected value is mu. So I've got 1/6 of mu plus 2/6 of mu plus 3/6 of mu, giving me 1 whole mu. So T1 is an unbiased estimator of mu. For T2, we do the same. So take the E in. So I've got 1/5 times the expected value of x1, 2/5 times the expected value of x2, and 2/5 times the expected value of x3. Each expectation is mu. So we have 1/5 of mu, 2/5 of mu, and 2/5 of mu, giving us 5/5, which is a mu. Therefore, T2 is an unbiased estimator of mu. We need to work out which is the better estimator. We need the one with the least variance. So we need the variance of T1 and the variance of T2. Variance T1, I square each coefficient. So I've got 1/36 times the variance of x1, 4/36 times the variance of x2, 9/36 times the variance of x3. Each variance is sigma, or sigma squared, as that's the standard deviation. So the variance of x1 is sigma squared, x2 is sigma squared, x3 is sigma squared. Add those up and we get 14/36 sigma squared for the variance of T1. T2, we square the coefficient. So I've got 1/25 times the variance of x1, 4/25 times the variance of x2, and 4/25 for the variance times the variance of x3. Each variance is sigma squared. So I've got 1 plus 4 plus 4, giving me 9/25 sigma squared. We need to work out which is the smallest. So either you make them both with the same denominator, and we can see that T1 is 175/18 times 25 sigma squared, or is equal to 0.3889 sigma squared, and T2 is 162 over the same denominator, or 0.36 sigma squared. So we can see, by comparing the fractions, we can see that T2 has the least variance, so T2 is the better estimator. It's closer, T2 will give you a closer value to the parameter mu. Now we need to write down a linear combination of x1, x2, x3, which will give an unbiased estimator with a minimum standard deviation. We have seen that T2 has an initial fraction with a smaller denominator than T1. So we had 1/5 and 1/6, and T2 gave the smaller variance. We need a smaller combination even than this. So let's try T3 to be 1/3 of 1 each of x1, x2, x3. So if we do an estimate expected value of T3 to show that it's an unbiased estimator, then we'll have 1/3 x1, expected value of x1, plus 1/3 expected value of x2, plus 1/3 expected value of x3. Each expected value is mu. Therefore, we'll have 3/3 of mu, giving me a mu. So T3 is an unbiased estimator of mu. Its variance, so we square the coefficient. So I've got 1/9 the variance of x1, 1/9 variance of x2, 1/9 the variance of x3. Each variance was sigma squared. So I've got 3/9, which is 1/3 of sigma squared. Now this is less than the variance of T2. Therefore, this is the smallest variance possible. So our standard error then would be the square root of the variance, which would be sigma over root 3. An estimation of the population mean. Suppose we have a random sample of n observations of a random variable x whose mean is mu and whose standard deviation is sigma. Then a sensible choice of statistic for estimating mu would be the sample mean x bar. We have seen from Maths Unit 4 that the sampling distribution of the sample mean has mean of mu. That is, expected value of x bar is mu. Then it's a standard deviation. It's an unbiased estimator of mu. X bar is an unbiased estimator of mu. We know that the variance of x bar is sigma square over n, x bar for a sample. We also need to remember that the mean of a binomial distribution is np and the variance of a binomial distribution is npq from Maths Unit 2. We're going to use that later. Okay, example 2. We have a table here. The discrete random variable x has the following probability distribution, where theta is an unknown constant. Theta is between 0 and 1/6 to make sure that the total probability becomes 1. In order to estimate theta, a random sample of n observations on x is obtained, and x bar denotes the sample mean of this random sample. Given that u, which is a times x bar plus b, is an unbiased estimator for theta, so we are told it is, determine the constants a and b and then the variance of u. So we need first of all to work out the expected value of x and the variance of x. So the expected value of x, being as it's a table, would be each x multiplied by its probability. Add them up, so we've got 1 times theta plus 2 times 2 theta plus 3 times 3 theta plus 4 times 1 minus 6 theta. Multiplying and expanding the bracket, I've got theta plus 4 theta plus 9 theta plus 4 minus 24 theta, giving me 4 minus 10 theta for the expected value of x. Now the variance of x we know to be e of x squared minus e of x all squared. So to find e of x all squared, we need to multiply each x squared by its probability and sum them. So I've got 1 squared times theta plus 2 squared times 2 theta plus 3 squared times 3 theta plus 4 squared times 1 plus minus 6 theta. So I got theta plus 8 theta plus 27 theta plus 16 minus 96 theta, giving me 16 minus 60 theta as e of x squared. So my variance is that minus e of x all squared, which becomes 16 minus 60 theta minus square the bracket and a minus outside, 16 plus 80 theta minus 100 theta squared, giving us 20 theta minus 100 theta squared. So we have those values as our expected value and our variance. Now we need to work out part A. So we need the expected value of u to be theta. It says it is an unbiased estimator for theta. Therefore, I put that the expected value of u, which is that combination, is equal to theta. I can take the e in, so a times expected value of x bar plus b is equal to theta. Expected value of x bar is also the expected value of x. Therefore, I've got a times 4 minus 10 theta plus b is equal to theta. Multiplying out, I have 4a minus 10a theta plus b has got to be equal to theta. We need them to be equal, so it's an identity. So I need to compare the coefficients. So my minus 10a must be equal to 1 for the theta. So a is 1 minus 1/10. And my 4a plus b is a 0 because there's no numbers on their own on the right hand side. So 4a plus b has got to be 0. So b has got to be 4/10 as a was minus 1/10. So b would be 4/10. Our variance for x bar, we remember that the variance of x bar is the variance of x over n. So there's the variance of x divided by n. So the variance of u would be a squared now times the variance of x, the variance of x bar. So it's a squared, which will be 1 over 100, times the variance of x bar, which is this. We can cancel some parts, cancel by a 10 and a 2, and we will get theta minus 5 theta over 5n on the bottom. Take the theta out, so I have theta times 1 minus 5 theta over 5n. That's the variance of u. So part B, let y denote the number of observations in the sample that are equal to 4. Given that v is the combination of c times y plus d, is also an unbiased estimate of theta, determine c and d, the variance of v, and show for c the quotient of variance of u to variance of v is that combination, so that we can see which one is the best estimator. So back to y. Y is the number of observations in the sample equal to 4. So the probability that x is equal to 4 is 1 minus 6 theta. If you call that p, then y has a binomial distribution with expected value of y being np, which is n times its probability, and the variance of y being npq, being n 1 minus 6 theta, and then 1 minus all that would be 6 theta. So expected value of v, I can take the expectation in, so it's c times expected value of y plus d. Expected value of y is 1 minus 6 theta. So we need to compare coefficients again. So the theta on the left and the right would have minus 6n equal to 1, giving us c would be minus 1 over 6n, and the bottom, the numbers being equal to 0, so cn plus d is equal to 0. C is minus 6n, minus 1 over 6n. They will cancel, so d is equal to 1/6. The variance of v would be the square, c squared times the variance of y, squaring the coefficient, ignoring the d. So c is now minus 1 over 6n, so the square of that would be 1 over 36n squared times 6n theta times 1 minus 6 theta. Cancelling the 6 and an n, I've got theta 1 minus 6 theta over 6n. So part C, I need to divide these two. So dividing them, I can see that if I flip the bottom, I can cancel a few things. The theta will cancel, one of the n's will cancel, and I'm left with the 6 will go up to the top bracket and the 5 will go to the bottom with that combination. If I multiply that out, I can see I've got 6 minus 30 theta over 5 minus 30 theta, which obviously will be greater than 1. Therefore, the bottom V would be the least variance. Therefore, V has the better estimator. Estimation of a probability. Let X denote the number of successes that will be obtained in n independent Bernoulli trials, each of which has a probability of success being theta, and theta we need to estimate. Therefore, we know that the X would be binomial, varies binomially with n theta, and the expectation of X is n theta, and the variance is n times theta times 1 minus theta. The proportion of successes, to estimate P, the proportion of successes would be the number of successes X over n, which is an intuitively sensible statistic for estimating theta. So that would be our expected value. So our expected value of P would be expected value of X over n would be expected value of X over n. So expected value of X is n theta over n, which is theta. Therefore, P is an unbiased estimator for theta. Its variance being, so X over n, the n would be squared if we take it out of the variance. So the variance of n of X would be n theta 1 minus theta over n squared. One of the n's will cancel, and I've got that combination. So the standard error of P is given by square root of the variance, the square root of that combination. But if we are using P for theta, so an unbiased estimator for the probability P of a successful outcome or proportion would be, so expected value of P would be, P for the sample would be X over n, would be our little p, and our variance of P would be PQ over n. So that's our expected value and variance for an estimation of a probability. Example 3. In order to predict the proportion of all votes that will be cast for a particular candidate in a forthcoming election, a random sample of 100 votes was canvassed, and 38 of them stated that they intended voting for the candidate. Calculate an unbiased estimate for the proportion of all voters who intend to vote for the candidate. Then find an approximate value for the standard error of the estimator used. So expected value of P would be the 38 out of the 100 possible, so 0.38. Our variance would be PQ over n now. So P is 0.38 times 1 minus that is 0.62 over 100, giving us that value. We need the standard error, so we need to take the square root of that. So we've got 0.0485 as an estimate for the standard error. It would be the expected standard error. So ESE, expected standard error of P, or estimated standard error of P. Example 4. Two pupils conducted experiments to estimate the probability theta that a particular type of drawing pen would alight point upwards when thrown onto a hard surface. The first pupil threw the drawing pens 300 times and the second threw it 200 times. Let X1 denote the number of throws by the first pupil that resulted in the drawing pin alighting a point upwards, and let X2 denote the number of throws by the second pupil that resulted in the drawing pin alighting point upwards. Show that those two combinations, T1 and T2, are both unbiased estimators of theta, and determine which one of them is the better estimator. So first of all, write down what you know. So X1 is distributed binomially with 300 as our n and theta as our probability, and x2 is also binomially distributed with 200 as n and theta as our probability. Therefore, expected value of x1 would be np. The variance of x1 would be npq. The expected value of x2 would be np for that one, and the variance of x2 would be npq for that one. So 200 theta, 1 minus theta. Therefore, we need expected value of t to be theta for it to be an unbiased estimator. So for t1, that combination we can take the expectation in. So it's 2 times expected value of x1 plus 3 times expected value of x2 divided by 1200. Expected value of x1 is 300 theta. Expected value of x2 is 200 theta. So we have 600 plus 600 giving us 1200 theta over 1200, which is theta. Therefore, T1 is an unbiased estimator for theta. T2 is this combination. So take the expectation in. We've got an expected value of x1 plus expected value of x2 all over 500. Therefore, so 300 theta plus 200 theta would give us 500 theta over 500, which gives us theta. So T2 is an unbiased estimator of theta. So now we need to work out their variances. So the variance of T1, we square the coefficients, so 4 times the variance of x1 plus 9 times the variance of x2 over 1200 squared. Each variance I substitute, so I've got 300 theta 1 minus theta for variance of x1, 9 times 200 theta 1 minus theta for the variance of x2. Multiply out, I have 1200 theta 1 minus theta and 1800 theta 1 minus theta. So I have 3000 theta 1 minus theta, so I can divide through, I can cancel, and I get theta 1 minus theta over 480. T2, I square the coefficient, so it's 1 over 500 squared, which gives us that. So variance of x1 plus variance of x2 inside the bracket. Variance of x1 is that, variance of x2. So I have 500 theta times 1 minus theta altogether on top. They cancel, leaving me with theta 1 minus theta over 500. Now obviously the bottom being the biggest, is 500, so that's the least variance. T2 has the smallest variance, and so is the better estimator. We have the top being the same, so we just need to look at the bottom of the fraction. Example 5 is an old WJEC question. 2 instruments are used to measure the concentration mu of a certain solution. Instrument 1 is such that the reading x obtained is a normally distributed random variable with mean mu and variance sigma x squared. Instrument 2 is such that the reading y obtained is a normally distributed random variable with mean mu and variance sigma y squared. It's required to estimate mu using the statistic t we have there, where lambda is a constant. Show that t is an unbiased estimator of mu for all the values of lambda. We'll do that first. Therefore, we've got x being normally distributed with mean mu and sigma squared of x as its variance, and y being normally distributed with mean mu sigma y squared as its variance. We need the expected value of t to be mu if it's to be an unbiased estimator. So expected value of t is the expected value of that combination. We can take the expectation in, this lambda times expected value of x, plus 1 minus lambda times expected value of y. Expected value of x is mu, expected value of y is mu. So we have lambda mu plus 1 mu plus lambda minus lambda mu, leaving us with mu at the end. So expected value of t is mu, therefore t is an unbiased estimate of mu for all values of lambda, because it's cancelled out. The variance of t is the variance of that combination. So we square the coefficients. So it's lambda squared times the variance of x plus 1 minus lambda all squared times the variance of y. Variance of x is sigma x squared. Variance of y is sigma y squared. Now they are constants. For a minimum variance, we need to differentiate the variance of t with respect to lambda and set it equal to 0. So it's lambda that could show the value of lambda which minimizes the variance. So we need to differentiate the lambdas. So differentiating that expression with respect to lambda, we get 2 lambda times the sigma squared of x. It's a bracket square, so it's twice bracket to the power 1 times the differential of the inside, which is minus 1, times sigma of y squared. And we need to set that equal to 0. Therefore, we've got 2 lambda sigma x squared minus 2. We have a minus, so minus 2 sigma y squared plus then 2 lambda sigma y squared. We need a value for lambda, so we can take the 2 sigma y squared over, divide by 2, take out the lambda and divide by the resulting bracket, and we have the needed expression for the variance of t, which would be the minimum, the variance of t. And that's the end of the presentation for Unbiased Estimators 1.